So we have started talking about the results on galaxy evolution studies in general field. First, we found out how the luminosity function seems to be evolving slightly, but now let's see some of the other results that have been obtained. A simple thing to do is to look at colors of galaxies as a function of redshift. And if we then predict what galaxies of different Hubble types would look like if there was no evolution, just a K correction, which you may recall from way back in Hubble diagrams, what would measurements look like given the redshifted spectrum? This is what it's like. The points are the actual measurements, and the three lines labeled with different Hubble types correspond to the colors that those particular Hubble types would have at a given redshift. And as you can see, the observations pretty much follow that band. So there isn't very much in terms of color evolution for the Hubble type sequence galaxies all the way out to redshift of unity. The Hubble Space Telescope has also afforded us another possible measurement, which is to look at galaxy sizes, say looking at their half-light radii or some other form of objectively defined radius. And so this is the result of what the radii, average radii of galaxies do as a function of redshift. Namely, galaxies grow in time. If the radii were fixed in proper coordinates, if there was no evolution at all, then a solid line shows what that would look like. But instead of that, the points show that there is a substantial growth of galaxies. This is consistent with our understanding of how disk galaxies seem to form from the inside out. As you'll recall, the bulge is the oldest part in the middle, then you have stellar disk, then hydrogen extending beyond it. That hydrogen has to turn into stars. And here we probably see the collective effect of that. Modern spectra of high redshift galaxies can be used to measure not just the redshifts, but also velocity broadening. In other words, get a velocity dispersion. With radii measured from Hubble Space Telescope, we can infer dynamical masses, or from fitting of the spectral energy distributions, we can infer their stellar masses. So that is shown here. The sizes of the symbols correspond to the magnitudes. We can see that the most massive galaxies seem to be already in place at redshift 1 or 2. This is sort of the upper envelope of this distribution, whereas the lower masses seem to be evolving. This is known as galaxy downsizing. Naively, you'd expect in hierarchical formation scenario that you make small ones first and then you gradually build the big ones, but that seems to be the opposite of what's observed. The solution to this is probably due to biasing effect we talked about earlier. We cannot wait long enough to see galaxies merge, but we can assume that some number of close projected pairs will eventually merge. So by doing statistics of close pairs of galaxies, allowing for projection effects and things like that, we can infer the likely merger rate as a function of redshift, and here it is. It's a power of 1 plus z, and it's more or less exactly what's expected from the modern models of hierarchical structure formation. You will recall that when we talked about scaling relations like the fundamental plane, I mentioned that they can be used as sharp probes of galaxy evolution. Luminosity function is a very broad distribution, but these correlations are by construction the sharpest we can have. And so if we can follow, say, the evolution of their intercept or maybe slope as a function of redshift, we can gain new understanding in evolution of galaxies, in this case ellipticals. What's shown here, the open points through which the line is fit, is the essentially zero redshift fundamental plane edge-on. The solid dots are ellipticals in one of the most distant clusters now known. And there are too few points, but you can see that they're consistent with being on a shifted version of the fundamental plane. Numerous studies have been now done, both for field and cluster ellipticals, and it was always seen that ellipticals at higher redshifts show a shift in the intercept of the fundamental plane in surface brightness that would correspond to the fading of stellar population in time as expected from evolution of stellar populations. And we can even say something about the star formation histories. we can fit different evolution models and find out which ones seem to describe the data the best. And the answer is that models in which elliptical galaxies form relatively early on and don't evolve very much since then, just passively fade away, seem to fit the data fairly well. That is shown in the plot on the left. The plot on the right shows fading, or if you look bit redshift brightening, surface brightness, which remember is related to the luminosity density of stellar populations, as a function of redshift. And you can see that it is systematically increasing in redshift for both field and cluster ellipticals. So these studies are consistent with what we've seen earlier, that as far as Hubble sequence galaxies are concerned, they seem to be pretty much in place by about redshift of unity. The ellipticals are evolving in the way we would expect from early bursts of star formation and relatively modest star formation history after that. And we also begin to see change in the tilt of fundamental plane, which really means that galaxies of different masses evolve at a slightly different pace. And it goes in the sense that those at the lowest mass end evolve fastest, which is, again, another example of that galaxy downsizing. That's as far as fundamental plane is concerned. What about Talley-Fisher? Well, that has been done as well, but turns out to be much more difficult and complex to do it for spirals at high redshifts, and these results are still not 100% clear, but they're at least broadly consistent with this picture. So far we looked at the evolution of galaxies in the field. What about clusters? This is a dense environment. You expect galaxy interactions to play some role. The first hint that something interesting is going on in clusters was so-called Butcher-Omler effect, established very early on. These two astronomers found out that clusters at larger redshifts seem to contain a larger proportion of bluer galaxies, for whatever reason. Generically, you expect that galaxy evolution leads from bluer galaxy to redder galaxy, so at least qualitatively, this seemed about right. Remember that in clusters, some merges will occur, but vast majority of interactions will not lead to merging. However, it will disrupt galaxies, may remove tidally some of their gas or stars, dark matter. And that's the process called the galaxy harassment. There'll be a lot of cumulative small encounters that would maybe remove gas from galaxies little by little. This would tend to transform late-type spirals and dwarf irregulars into S0s and ellipticals in time. With the Hubble Space Telescope, it became possible to look directly at a morphology of galaxies in distant clusters. And here is one of them, where different symbols correspond to galaxies of different morphological types. With that, and spectroscopic measurements, we can try to disentangle what's going on. An interesting finding was made that there is a novel type of galaxies found in these evolving cluster populations, so-called post-starburst galaxies. Galaxies that are bluer than they should be at zero redshift if there was nothing happening, and have spectral energy distributions consistent with having undergone a burst of star formation maybe up to a billion years earlier. This could have been caused by some interactions, and these galaxies would then presumably fade into redder Hubble types. And so the summary of these results is that, as far as we can tell, there is a conversion of late-type spirals into S0s and ellipticals in the clusters. This is related to density of clusters as well, the morphology density relation, and that can account for the observed Butcher-Omler effect and presence of things like E+A or post-starburst galaxies. So one possible scenario is that spirals from field are falling into cluster potential well. As they do that, they encounter dense intra-cluster gas, the X-ray gas. Some of their own gas gets stripped away that quenches the star formation in them. They may undergo a burst of star formation triggered by some of the interactions, but eventually that fades too. And in the end, you may have an old disk like S0 galaxy. So this is a plausible scenario. This is not necessarily the only way to make S-zeros, but it can account for the observed effects in clusters. Next, we will talk about the obscured component of star formation history in galaxies.